All right, guys, so this is going to be the second part, or part two, of this morning's lesson. All we're going to do is make the equations a little bit more complicated, that's all, okay? So, I think this here, sorry, one second, just something catching my eye and I mistyped it. Okay, this is a milliliters per second, okay? I think I hit the slash key twice, okay, obviously. So, let's take a look here. So the volume of a cylinder is increasing at a rate of 30 milliliters per second. The cylinder has a radius of 6 centimeters, okay, and a height of 10 centimeters. How fast is the level of the liquid rising? Okay, well, how fast is the level of the liquid rising? Okay, well, it sounds like, if I were to think about this, that last question there is talking about how well, we could relate that to the volume changing, right? So we could say, okay, well, if the level of the liquid's rising, obviously the volume of water in the cylinder is increasing as well, right? So we could say, okay, that's going to be our equation that we're going to relate to this scenario. So we could say, okay, well, what is the volume of a cylinder? Well, the volume of a cylinder is equal to pi r squared h. Okay? And so what we could do here is differentiate, right? Ultimately, what we want to do, we want to say, I think what helps sometimes is differentiating first, and then once you have this big long line of differentiated variables, you could go back to the question and try and like write a list of knowns and unknowns down here on the side, and plug in your information accordingly. So that's what we're going to try and do here. This is like kind of a little approach, right? So ultimately, we're going to have, we could see the volume of the cylinder is increasing at a rate of this, right? So we can see, okay, well, we know that the volume is changing. And so if we were to derive the volume with respect to t, time, that would be equal to, okay, it's important to keep track of what you got on the side. We have an r variable and we have an h variable, okay? Two separate things, just like when we had two functions multiplied by each other, right? The pi is irrelevant. It's sitting out front. You can almost even ignore that, right? And we'll just multiply it by at the end. Okay, so let's differentiate this, but keep in mind, this is going to be like a product rule, right? So we're going to differentiate with respect to r first, right? We're going to find f prime, because this is r, and g of x is the h function. Well, that looks like an n. H, okay? So we're going to differentiate. So let's do that. So we're going to get 2 pi r multiplied by, and chain rule says, okay, well, I'm differentiating with respect to time. There's no time or t variable, so I have to write dr by dt, right? And then I have to multiply that by the original h function. Okay, now product rule is telling me, okay, well, now I have to add the original f of x function, so basically pi r squared, right, multiplied by, I'm going to move these over so they're not in the way. We're going to multiply by h, the derivative of h, sorry. Just having a little. The derivative of h is going to be 1, and then multiplied by dh by dt. Okay, and all this is multiplied together. Okay, so let's write now. We have a whole bunch of information. This means, and we can kind of try and interpret it, right? This is how the volume is changing with respect to time. This is how the radius is changing with respect to time, which hopefully raises a red flag with you. H is just the height of the cylinder. R is the radius. dH by dt is changing with respect to time. Okay, so let's think about this. We know how the volume is changing from the question. It's 30 milliliters per second, right? So we know dV by dt is going to be 30 milliliters per second. We know the cylinder has a radius 6 centimeters. Okay, and I'm just trying to go left to right too, I suppose. I'm just having an eye at that, right? The next thing here is dr by dt. And when I said this, hopefully this raised a red flag for you. You know, this is a fixed cylinder, right? The radius is not changing, right? So this is equal to 0. Right? It's a fixed cylinder. You can't just decide to change the radius, right? If it was a cone, like maybe what we see in the next question, the radius is changing as the height changes, then that would make sense. But for a cylinder, the radius is constant the whole way up. It's not changing, right? And so the rate at which the radius is changing has to be 0, right? Logically. Okay? Pi, we know what pi is. H is telling us, okay, we're interested in when the height is 10. So h is going to equal 10 centimeters. And ultimately, we want to find out how fast is the level of the liquid rising. That is dH by dt. That's what we want. Okay? So now we can just go back over to our equation that we've created using differentiation implicitly. Okay? And we can plug in all the information that we know. Well, we know if we plug in, we know if we plug in this rate value of 0 in here, I'm going to get 2 pi r times 0 times h. Well, this whole term is going to disappear because of this 0. Okay, and so we're going to be left with the fact that dV by dt, how is the volume changing with respect to time? Well, that's going to be pi r squared dH by dt. Okay, so let's plug in our numbers. Okay, so we can say, okay, well, the rate at which the volume's changing is 30. That's equal to pi is 3.14159, we could say. We'll leave it as pi for now because you guys have a button. And then times r is 6. And remember, I was just worried here. How did the height come into play? Well, the height apparently didn't matter with this question, right? I was just worried about that. But it takes care of itself, right? When you plug in everything. Okay, and we get dH by dt. That looks horrible. This is what we're after. Okay, so we say, okay, well, dH by dt is going to equal, oh, sorry, and there's a squared there. Sorry. Okay, dH by dt is going to equal 30 over 36 pi, which is going to equal 5 over 6 pi. Call that, what are we looking for? Meters per second will be the units. Centimeters per second, sorry. Okay, guys? You could type that in if you'd like, but it's always nice looking, instead of having all these decimal numbers and things like that, it's nice looking at that too, okay? The exact values. Okay, not that bad. I would say the hardest part of this is selecting an equation to relate everything in the question, right? But hopefully my goal is today to do an example with you for all of the questions that you're going to see. Okay, if that's a cone, a cylinder, a hemisphere, circle, square, we're going to see some Pythagorean theorem questions later this afternoon, right? You're just selecting one of the equations that you've had some experience dealing with in the past, as far back as grade 4, grade 5, right? And applying your derivatives to it, implicit differentiation. That's what's cool about this, okay?